This elevated water tank works because elevated mass creates reliable pressure. The clever bit here is using height. Instead of running high-power electric pumps every second, municipal utilities pump water high into massive overhead steel storage vessels. The heavy weight of that raised water column maintains steady physical pressure at every ground-level household tap in town. This static hydraulic head ensures immediate clean water delivery whenever someone opens a faucet, buffering against sudden morning domestic spikes. However, relying solely on simple tower height creates an immediate operational challenge when thousands of residents start their morning routines simultaneously across town. When every household opens faucets at the exact same moment, localized fluid friction inside long underground distribution pipes causes line pressure to drop noticeably. A simple elevated storage vessel model assumes static liquid, but real-world distribution pipe networks experience substantial dynamic head loss during high peak flow hours. If pipeline pressure drops too low, external groundwater and contaminants could potentially infiltrate aging pipe joints, compromising the municipal drinking water safety. For safety reasons, do not encourage climbing, opening, contaminating, or modifying a public water tank or any connected municipal water infrastructure under any circumstances. To prevent low-pressure contamination, civil engineers calculate minimum operating water levels and elevate the tank high above the highest residential neighborhood elevation. Official EPA guidance confirms that finished water storage must maintain adequate distribution pressure while supporting daily peak demand variations throughout the service network. By elevating the tank structure high enough above the town, static hydraulic head comfortably overcomes standard pipe friction losses, maintaining strong positive pressure across all distant neighborhood taps. Ground-level electric booster pumps refill the overhead tank during off-peak night hours when electricity rates are lower and overall community water demand drops dramatically. This continuous operational balance buffers the municipal power grid while supplying steady, reliable domestic water flow during normal daily operation throughout the entire city. However, static elevation calculations designed for normal domestic taps usage cannot automatically handle sudden, massive, high-volume emergency water demands across the municipality. The bigger problem is surviving sudden catastrophic water draw events, such as emergency firefighters fighting a massive multi-alarm industrial building fire. When commercial fire hydrants draw thousands of gallons per minute, direct pumping water systems experience immediate severe pressure collapses across the entire distribution network.
Sizing continuous inline electric pumps to handle emergency fire flow requirements directly would require extraordinarily large, hyper-expensive motors that sit idle and underutilized most of the time. Running massive, oversized pumps intermittently causes extreme electrical grid power surges, severe mechanical pump wear, and dangerous water hammer shocks inside buried city pipes. Furthermore, widespread power outages during severe lightning storms would instantly leave firefighters without distribution pressure if the water network relied entirely on active electric pumps. Municipal engineers needed a completely passive mechanical buffer capable of discharging immense emergency flow rates instantly without relying on active electrical grid power. To solve this, engineers recognize that actual network pressure depends on elevation, demand, pipe losses, control systems, and overall utility design working together. The elevated storage tank operates as a giant hydraulic battery, storing immense hydraulic potential energy during quiet, off-peak operational periods throughout the day and late night hours. When fire hydrants open unexpectedly, gravity instantly forces stored water down the large vertical riser pipe without waiting for electrical booster pumps to spin up. EPA public water system training modules emphasize that finished water storage pressurizes distribution networks, meeting critical peak use periods and supporting vital fire flow capacity. The wide horizontal cross-sectional area of the elevated bowl minimizes vertical water level drop during rapid, high-volume emergency discharge events across the municipal service area. By establishing a high, consistent hydraulic grade line, gravity maintains reliable positive distribution pressure across both elevated hilltops and low river valleys equally. Automated telemetry control valves continuously monitor pressure sensors situated throughout the underground distribution network to regulate local ground booster pump stations smoothly. When electronic level sensors detect a drop inside the elevated bowl, ground pumps automatically engage to refill the storage reservoir smoothly and efficiently over time. This clever mechanical architecture decouples peak flow demand from pump capacity, allowing smaller, far more efficient ground pumps to operate continuously at their peak electrical design efficiency. Heavy-duty internal altitude valves prevent accidental tank overfilling, closing automatically when the internal water column reaches its engineered maximum target height. Maintaining continuous positive pressure prevents dangerous backflow and back siphonage, protecting clean municipal drinking water from external soil contaminants and hazardous chemicals. Engineers calculate overall head loss by simultaneously evaluating pipe diameter, internal pipe wall roughness, elevation changes, dynamic friction losses, and peak flow velocity.
Because gravity functions without pause or electrical dependence, the elevated storage tank delivers immediate high-pressure fire suppression water even during total municipal grid blackout emergency events. Utility engineers carefully balance physical tower height, system control valves, pipe sizing, and reserve storage volume to optimize long-term municipal water distribution safety and operational efficiency. This passive hydraulic engineering approach significantly reduces mechanical stress on pumps while guaranteeing an immediate high-volume response to catastrophic emergency water demands. The elevated water tank effectively transforms intermittent electrical energy input into smooth, dependable, continuous kinetic water pressure for every home in the community. In conclusion, elevated water tanks provide an elegant, time-tested physical solution to complex municipal fluid dynamics, urban infrastructure planning, and energy management challenges. By raising finished water high above the town, water utilities harness constant gravity to maintain safe, reliable, positive pressure across diverse geographical topographies. The stored overhead volume seamlessly absorbs extreme peak demand surges from daily taps and emergency hydrants without requiring oversized, energy-intensive continuous pumping stations. This balance of stored potential energy, smart control valves, and physical elevation protects public health by keeping clean drinking water flowing safely day after day. Through fundamental physics and thoughtful utility design, elevated water towers ensure dependable, grid-independent water pressure at every tap across the entire community.